Welcome back to the International Consortium of Advanced Technologies and Security beginning curriculum course for Thermography Level 1 certification. This course is an introduction to thermodynamics. This is Module 3. So how does all of this apply to the thermographer? How do you use this information in your work as a thermographer and in the field? It is useful to understand what we are seeing and how we're seeing it, why we're seeing it, because by the time the device or the mass that we are looking at has sufficient energy to, say, glow red, that is, into our visible range, it is usually too late to do anything about it. While that is not always true, it is 99% of the time. It wasn't true, for instance, on the USS Kitty Hawk in 1991 when we found an aircraft elevator which they wanted us to examine, and when they just turned the power on the elevator as we were cooling off the dewar on the large camera that we had at the time, pouring liquid nitrogen into the dewar. Dewar is the holder of the liquid nitrogen, and warming up the large computer that was worn on the chest. It was a very large device, Thermal Vision 570 or 580, I believe. We could see the contact was starting to glow red. Now, in that case, very little needed to be done. The device literally needed a large nut and bolt loosened and sandpaper put inside, cleaned off, blown off, and then reassembled. But usually, but that's a very, very large contactor. The contactor itself probably weighed several hundred pounds. That was a very large elevator. Of course, it's lifting aircraft onto the flight deck from the hangar bay. So that's a very large device. Most devices you see will not be that large, and so we want to catch it well before it gets to that range. In thermography, we're looking at the spectrum of light outside the visible range. The camera separates these energies and assigns artificial colors to those spectral ranges and energies given off so that humans can see those differences. So the thermogram is an artificial representation of the thermal energy given off by the subject that we see in the viewfinder of the thermal imaging device. This NASA illustration illustrates the various wavelengths of visible light and others, that shows pretty much a good piece of the electromagnetic spectrum. And showing it, NASA uses infrared for spectroscopy, which is compiling different ranges of light together to study objects from space, so it can tell specific kinds of subjects by the frequencies of light it gives off. Not just one frequency or a narrow range, but all of the light range. That's what spectroscopy is. The light range, the light ranges of infrared are generally considered to be 0.76 to 0.9 nanometers. A nanometer, expressed usually as a mu, is a nanometer is a billionth of a meter. So it's less than a billionth of a meter long. That is, a wavelength is measured from the peak of one wave to the peak of the other wave. That is a wavelength. So again, the near infrared is 0.76 billionths of a meter to 0.9 billionths of a meter long. A little above that, or that and up, is from 0.91 billionths of a meter, or nanometers, to about 2.35 nanometers is the mid-infrared range. The range we're concerned with is 10.4 to 12.5 nanometers. That's called the thermal range, the thermal infrared area. That's given off sheerly as heat. It doesn't just absorb, it actually warms things up when it goes into them. Okay, so remember, the hotter something becomes, the shorter the wavelength of light that it emits. So the infrared device does not need to see the entire infrared range. It's a scientific instrument that performs its job very well, enabling visualization of the heat normally outside the visible range or visual range of humans. The visual range is the colors that you see there that are visible to the human eye, of course. Infrared is not. In thermography, we apply thermographic principles when we examine a device. And many of those are built into the device itself. Many we used to do by longhand, by very long equations, are now done internally by the device or by the software you use for analysis. However, you must be aware of the reasons you are seeing these phenomena and look through why and how the heat is reaching you to figure out what the problem itself is. In thermodynamics, we think about the quantities which describe the system we are looking at. The volume of temperature, the pressure of the gas, tell us something about the system and the work it can do. If you're an engineer and working on a machine that you're trying to do, these are very important. If you're trying to analyze what's wrong with the device, you still need to understand those. Electromechanical systems do work and therefore have waste heat, which is not an issue normally, except it may be, like as before, an environmental issue. You may be heating up the environment that it's in, or it may be a problem with the efficiency of the engine. Or you may have a fault, something that's going wrong with the machine, and that's where we come in. In thermal imaging, we're dealing with what is hot, why it's hot, where the energy is coming from, how did it get to our imaging device. Is it a simple image? Is it a complex image? Is the device simple? Is the device complex? We must differentiate between the heat that is normal and the heat that is the indicator of a problem, as it was in this image. This image is a motor which is off to your left, an electromechanical device that is driving a different device. This is probably driving a fan. I forget at the time, I'm sorry, but it's probably driving a fan. But intermediate to that, between them, is just simply a bearing that's holding the pulley, because the belts pull a lot of pressure on it. You don't want that pressure on the pulley. You don't want the pressure on the motor. You want the pressure on something intermediate to that. And here we do see a problem. You'll notice in the thermogram aspect of that, the right side is a little bit hotter than the left side. So this is probably a misaligned pulley that is pulling angularly on this bearing and causing it to overheat. So we need to understand what's causing the heat, why it's causing the heat, and according to the specifics of that device, how do we repair that? What do you need to do to stop this problem? The problem is, of course, that the lubricant inside here has a specific range of heat it can operate in. Then it starts slowly breaking down, or it increases the breakdown. It slowly breaks down anyway. Any kind of a carbon atom will break down over time. Okay, but in this case, you have a lubricant in here. The lubricant is added, it's maintained, it's changed once in a while, but it's becoming hot, so it starts breaking down faster the warmer it is, and if it gets to a critical point, that will break down, causing this to seize up and this device to stop working. We need to remember and to ask in every case, what is it we are seeing? Why are we seeing it? Why are we seeing that heat generated? And what path did it take to get to us? What caused this condition, or is the likely cause of the condition? And is this normal or abnormal? Every abnormal heat condition is a problem. Remember, heat is thermal energy transferred from a region of high temperature to a region of lower temperature. Remember the zeroth law, the second law also? Okay, it's flowing down the thermodynamic gradient. It's always seeking to obtain thermal equilibrium. Okay, in this case, you don't want it to. You don't want your whole space this hot. You want to find this problem, identify it, fix it before that problem becomes an issue, because it will become a fire long before it equalizes the heat in this space. Heat is thermal energy in transit. Heat is easily detected using a thermal imaging device. Here we have a problem that is merely 11 degrees over ambient, so it's an intermediate problem. But what caused this? And in this case, the hottest spot is where that little the little plus sign, if you can see it, to the left side, but not at the end of the blue line, is the actual problem area itself. It's the problem of highest heat that we can see, because again, where the connector itself is a little more complicated. So when it wicks to that particular point, we can see the heat is the connection itself. It needs to be probably taken apart and cleaned and tightened. At times you can just tighten these and the problem will go away.